All right, for this final problem, you're going to want to try it out, but review that page about psi because we're going to need it for this one. All right, we've got another situation where we've got an arm forcing something forward, and so it has its own force acting perpendicular to itself, right? And something like that, acting perpendicular to this forked rod or slotted arm, they call it. So that would be its force, but there's also a normal force caused by the um, the circle, right? So if you look at its tangent path, let me change color here. If we look at the tangent path, it would be something like that. And so perpendicular to that tangent path, we will have a normal force, right? That normal force is not in the r-axis, right? The r-axis would be drawn by going from the O through the particle and continuing. That's our positive r-axis, if you recall. And our positive theta axis would be in the counterclockwise rotation direction perpendicular to r. So that would be perpendicular like that. Right? And this is not, oh, definitely not that one. Not the easiest thing to see here, but in the end, the force here, let me redraw that one. The perpendicular to the arm is in the theta axis, but um, the normal force caused by the circle is not in the r or the theta axis. So we're going to need that psi to be able to break that into components and decide how much is in each axis. There we go. So this is what I was trying to click, but it wouldn't let me for some reason. Well, I'll let the slides do that because it's going to get neater here. All right. And they did give us theta is 60, theta dot is 5 radians per second, which is constant again, so theta double dot would be 0. They gave us an R equation that we can use for a derivative. They also have this stretched chord, which is interesting. That's going to come into play here in a little bit. So let's come up with our kinematics, chapter 12 stuff, right? R dot with a derivative, a little bit of a chain rule, R double dot, chain rule with product rule again. Plug in theta equals 60, theta dot equals 5, and theta double dot is 0. We've got R dot, and R double dot, as well as all of our thetas, so we can plug into our equations, turn the crank, and out pops our R acceleration and our theta acceleration. So nothing new there. Hopefully that's getting familiar now. Now this is the part where we got to be extra meticulous with our drawings, okay? So I'm going to escape here so I can zoom extra and show you what's going on here. So first, let's draw our axis, right? We need to go from the point of rotation, O, through the particle, and that's the direction of our positive R. So there it is, positive R in that direction. And then theta is perpendicular to that in the direction of the counterclockwise rotation, right? So that would be rotating counterclockwise. So that's the positive theta. Okay. So now it's important that we put in this tangent path, right? This is a critical part of these types of problems now. So the tangent path, if we were to zoom in, that's tangent to the surface of the circle, right? Would be the pathway that our little particle is going on. So at this instant where theta equals 60 degrees that they gave us, there's our tangent path, right? This isn't 60 degrees, right? This isn't 60 degrees. 60 degrees is what theta is. What we care about for the tangent path, though, is just, right, tangent to the pathway of the particle, which would be going around the circle. So draw that on there. And now that's going to help us to come up with the directions of everything else. So the forces on it, right? Luckily, they told us this is a horizontal path, so we don't have the weight of the particle in here. But we do have a couple other forces, right? We've got this elastic spring force, Fs, right? The more this stretches, the bigger it gets. And so that's just going straight in the direction of the arm, which puts it squarely in the r-axis, right? So that one's easy. We also have this slotted arm forcing it to go around, right? So that one, you can only push with a force perpendicular to itself, right? So that's as it goes around, right? That's always going to be perpendicular to the arm. So we can draw that force perpendicular to the arm, which if it's perpendicular to the arm is on the r-axis. That puts the force of the arm, F, squarely in the theta axis. Right? So those are nice and clean. We like those ones. Now there's one other force, which is the normal force that keeps the ball from falling inward on the circle, right? The surface of the circle pushes outward with a normal force wherever that ball rolls along it. So normal force means it's perpendicular to that surface. And we defined that surface with this yellow tangent line, right? So perpendicular to the tangent line would be this normal force that it pushes out on the ball with. Right? So that's the one where we have to think, how are we going to handle this? That is neither in the theta nor the r-axis, right? So not as clean cut as the F and the spring force. So that's where this psi comes in, and we defined that earlier as the angle between the tangent and the r-axis, right? And so if we calculate that, then we can use that to relate in to the axes, right? We need some angle, so we can use sine and cosine to split it into its two components in the r and the theta directions. So we'll calculate that later, but what I want to show you is that this can be more useful than the way it's drawn on there if we use a little bit of intuition here to come up with a, um, a different angle here. So if I, instead of using that angle, right, that's not super useful. I need to relate in to the axes. But what I can do here is I could say, oh, okay, well, if this is 90 degrees, right, from here to there, that's 90 degrees total. Well, then this is just 90 minus psi, right? But if this is 90 minus psi, well, then this also adds up to 90. So this would be 90 minus 90 minus psi. We get psi again, right? Because this also adds up to 90. So this adds up to 90, this adds up to 90. Therefore, this angle here has to be psi. And that's a lot more useful to know this angle directly. I don't have to do 90 minus psi or anything. I can just say, okay, yeah, I've got I've got negative in cosine psi in the theta direction, and I've got positive in sine of sine of psi, tongue twister there, in the r direction, right? So with that, we should be able to do our sum of the forces and take care of everything. So let's jump on it. We can now, let me clear that guy. There we go. We drew it up, and really that's the bulk of the work here. Right? If you can draw it, you can get the rest successfully. I have faith in you, in your math skills. So the spring force, we'll need that. Let's calculate it. Then we'll plug and chug everything. So the force of the spring is the spring force K times some change in length S. They gave us 30 newtons per meter at the beginning, right? 30 newtons a meter is our K. It was originally unstretched at 0.25, and it's stretched to some distance. If only we had a way to measure that R. Oh, we do. They give us an equation for R, right? Otherwise, maybe we'd do some trig and we can figure it out. But R, plug in theta equals 60. We already actually did that on the previous slide. We got 0.6928 meters for R. So that's our final stretch at this instant. That was our initial length. So that's our change in length times 30 newtons per meter. We get 13.28 newtons for our spring force. We're also going to need that angle psi. So this was the equation we derived earlier. We could solve that by finding R, which we did, right? R is 0.8 sine theta, plug in 60. We've got R is 0.69, whatever it was, 0.6928 meters. Now we need to do dr d theta, which if R, excuse me, is 0.8 cosine theta, then dr d theta is just d theta of that, right? Which there's not a lot of work shown here, but 0.8 cosine theta, take the derivative of that. In terms of theta, you'll just end up with negative 0.8 sine theta, right? Plug in cosine theta, and you've got, oh, no, I'm doing some voodoo here. This is our R, 0.8 sine theta. You'd end up with 0.8 cosine theta. So they already did the derivative there, 0.8 cosine theta. Plug in 60 degrees and you get 0.4. So why don't we have a chain rule here? Well, it's because we're doing this in terms of theta, not t, right? When we did theta dot or r dot, we needed chain rules because theta was inside of the function and theta was a function of time, right? But here we're not doing dr dt, we're doing it in terms of theta, right? So this would be like dy dx in our equations in x. There wouldn't be any chain rules involved there. It would just be a regular old derivative, just like this one. So we've got that now. We solve the inverse tangent for this equation to solve for psi, and we end up with 60 degrees for psi. And now they're being a little funny and making it 90 minus, but we decided, yeah, let's just use that other angle psi rather than 90 minus it. But either way, whatever makes sense to you. We just need to have some angle there so that we can do this next step, right? So we'll go with their 30 with the 90 minus side just to do our equations the same as what they've got, but you could just as easily do sine of 60 instead of cosine 30. So if we know that that is 30 degrees, we can sum the forces equals ma. In the r direction, we've got in cosine 30 going positive. We've got negative force of the spring, which was 13.28 newtons, equals mass of 0.08 kilograms times the acceleration in the r that we calculated a second ago. Same in the theta direction, we've got F going in the positive. This looks like it's to the left, but it's in the positive theta direction, so don't get turned around there. And then we've got in sine 30 going in the negative theta direction, because it's the positive direction, equals mass times acceleration that we solved for earlier. And solve those two, you get in and you get F, and that's a beautiful thing. So that is it for that problem. Definitely an important one to figure out how to solve for psi and apply that in the right place on your drawing, relating your tangent path to your other forces. That's a critical part to getting that right, is getting the drawing good.